Hey guys, Mr. Betts here. Before you watch this video, try to complete this page and the next page before I go over it with you and see how you do on your own. And so go ahead and pause the video, finish them if you haven't had a chance to, and then play the video and we'll go over it together. So the idea of this page and the next is to kind of look at how we're going to phrase the meaning of different things in the context of calculus problems. So generally what we're going to look at is the meaning of the value of a function and the meaning of the value of a derivative. So in the example here, the function v of t gives the volume of water in a tank after a certain amount of time. So when we plug a value into that function, it's simply just giving us a volume. So v of 3 equals 20. We want to make sure we explain not just what the 20 means, but also what the 3 means in the context of the problem. So v of 3 equals 20 is telling us that at the point where t equals 3 minutes, so after 3 minutes, there are 20 liters of water in the tank. So v is measured in liters. So notice that we're explaining what the 3 means with units. We're explaining what the 20 means with units. Then in the second part with the derivative, remember a derivative is a rate of change. We still want to explain what the 3 means, and 3 is still a t value. So that 3 is still telling us what happens after 3 minutes. But then v prime is telling us how fast v is changing. So v is measured in liters. How fast it's changing, we're going to divide by minutes. So we're going to get units that are liters per minute. I do want to point out that we have a blank here that is basically indicating whether volume is increasing or decreasing. So we're going to take the sign, that negative in front of the 2, and use that to indicate whether the volume is going up or going down. So we want to interpret not just the number, but also the sign of the number. So the volume is going to be decreasing at this point at a rate of 2 liters per minute. So notice that we didn't put the negative on the 2 here because we indicated what that negative meant by decreasing here. It would be wrong to say that the volume is decreasing at a rate of negative 2 liters per minute, because that would actually indicate that it's increasing. I also want to point out that we're not going to say the volume is changing at a rate of negative 2 liters per minute, because we want to make sure we understand what that negative means. So we're not really ever going to say changing. We're always going to use words like decreasing or increasing. Okay, so let's jump into number 1 here. Number 1, we have the area of an oil slick given in square kilometers after t hours. Kind of a grim model here. So we have oil on water, probably not a good thing. So A is measured in square kilometers, T is measured in hours. So A of 24, so first of all, that 24 is telling us after 24 hours. Okay, so at the point that 24 hours have passed, the area of the oil slick is 17. And remember, we want to make sure we include units, so it's going to be 17 square kilometers. The second part with the derivative, we're looking at how fast the area is changing. All right, so we want to indicate what the 5 is with units, what the 4 is with units, and whether that derivative indicates an increase or a decrease. So starting with what the 5 is, remember that's a time value measured in hours. So after 5 hours have elapsed, the area of the surface of the oil slick is it increasing or decreasing? Well, the derivative is positive, so we're going to say it's increasing at a rate of 4. And 4 is going to be measured in units for a derivative here, which is going to be the area per time. So square kilometers per, and time is measured in hours. So square kilometers per hour. You could write these units like this with the per in there. It's also acceptable to write it as square kilometers per hour as a fraction. I know that box is kind of short, so you can use a slash to do that if you want. Number 2, we have the cost of digging a hole. Seems to be a maybe some sort of drilling operation, maybe a fossil fuel theme here with this worksheet. So the cost of digging a hole that is X feet deep, hopefully it's prohibitively costly, so we don't do it at all. So again, we want to explain what the 20 means when we plug it into the function itself. So 20 is the x value, tells us how deep it is. And then the 140 is the cost. So they're actually kind of switching things up here. They're telling us the cost first. So it costs $140 to dig a hole that is 20 feet deep. Then the derivative is telling us how fast that cost is changing. And so we want to know how fast it's changing when we plug 20 in for x, so the depth. So basically, as we dig deeper, is it costing us more or is it costing us less? So the depth of the hole, it looks like, is coming first. So when the hole is 20 feet deep, the cost of digging is it cost going up or is it going down? So the derivative is positive, so it's increasing at a rate of 5, and we want to make sure we get the units right here. So we've got cost measured in dollars, and then the independent variable x is the depth measured in feet. So it's going to be $5 per foot. Number 3, we have the acceleration measured in centimeters per second, or centimeters per second squared. And that's given after t seconds. So if we plug 2 in for t, that means after 2 seconds. So that's the input into the function. The acceleration is, so the acceleration is given by this value here. Notice that -6 does not mean the acceleration is decreasing. It just means that that's what the acceleration is. So the acceleration is -6, and then centimeters per second squared, because that's just what the units are measured here. With the derivative, now we're talking about how fast the acceleration is changing. For you physics people, you may know what this is called. The change in acceleration is jerk, kind of a fun name for physics. So if you're sitting in a car and you accelerate really quickly, that jerk that pushes you into your seat is partly from acceleration, but the change in the acceleration is what you feel on that initial push. So anyway, after a certain amount of time, so after 7 seconds, because that's what we're plugging in for t, the acceleration is, so they're making us do all of this now. So acceleration is changing, and it's the change in acceleration is negative. So the acceleration is decreasing, and it's decreasing at a rate. So remember, derivatives are rates. So it's decreasing at a rate of 3. And then we're going to divide acceleration units by time units. So 3 centimeters per second squared per second. Or we could say 3 centimeters per second cubed. I've mentioned before, squaring time units doesn't really have an intuitive meaning. So if we cubed time units, that would also not have much meaning for us. So now on the back, they're making us do more and more on our own. So P is giving the population in billions of people of the world after 1950. P of 40 equals 5.3. So 40 years after 1950 is going to be the year 1990. So in the year 1990, the population of the world, and we'll use past tense because that was in the past, was 5.3 billion people. I want to make sure we include units there. The derivative. So the derivative here, remember this is just a t value, so we'll start by saying what that 60 means. So we'll say in the year 60 years after 1950 would be 2010. So in the year 2010, the population of the world was, so it was changing, given by the derivative, but we want to say whether it was increasing or decreasing. So the population was increasing at a rate of, so I'm not a big fan of saying 0.078 billion. So it wouldn't be wrong to say that, but I would actually convert this to something that would be a little bit more meaningful. So if 0.078 billion, if it's 0.078 billion, that's going to be the same thing as 78 million. So I'm going to use that just because it makes a little bit more sense. You certainly wouldn't have to make that conversion. So at a rate of 78 million, and remember, this is a derivative. So derivative is going to be a rate of change. We've already indicated a rate here, but we want to include units, which is going to be people per, and then time units are measured in years. So people per year. So in the year 2010, population was increasing at a rate of 78 million people per year, or you could say 0.078 billion people per year. Number 5, we have R giving the rate in pints per second that oil is flowing into a tank after T seconds. So R itself is a rate. We want to keep that in mind. And the units for R indicate that it's a rate. So R of 10, so 10 is telling us when, that's a time value. So after 10 seconds, or you could say when 10 seconds have passed, or at the moment that 10 seconds have passed. So after 10 seconds, so now that 3 is telling us, remember R is a rate, so 3 is telling us a rate. So oil is flowing into the tank at a rate of 3, and then we want to include units. R is measured in pints per second, so 3 pints per second. So remember, R is a rate. When we take the derivative of that rate, we're going to figure out how fast that rate is changing. So at t equals 10, the rate is 3 pints per second, but that rate could be changing. So the flow into the tank could be increasing or decreasing. So when we take the derivative, we're going to have pints per second, and so that's going to be the units we would expect on the derivative of that rate. So first we want to explain what that 6 means. So we'll say after 6 seconds, the rate, so R is decreasing. R represents a rate. So the rate that oil is flowing into the tank is, the negative means that it's decreasing. So the rate is decreasing. Okay, so you can just think of this as oil's flowing into the tank, but the rate that it's flowing in is slowing down. So it's decreasing at a rate of 0.2. Again, notice that I didn't put the negative with that because we already said it's decreasing. And then the units on the rate of change of that rate will be pints per second per second. Okay, so if the rate that oil is flowing into the tank at t equals 6 is, say, like 7, then a second later we would expect it to be about 6.8, assuming that this rate, this derivative here, is staying pretty close to the same. So the last part here, we have the function v, and we want to write what derivative would answer the question for each one of these. So in the example, it says after 3 minutes, the volume of water in the tank is decreasing at a rate of 8 liters per minute. So the derivative that would indicate, it's saying the volume is decreasing at a particular rate, 8 liters per minute. So volume is changing. That's where the V prime came from. At what time is where the 3 came from here. And then what that rate is, since it's decreasing, it's going to be negative, and then 8 liters per minute. So notice that we don't put the units on there, although it wouldn't be wrong to put units on that derivative. So on number 1, when 7 minutes have passed, the instantaneous rate of change of water in the tank is 12 liters per minute. So the amount of water in the tank is measured by V, but V is changing. So it's going to be V prime, and it's when 7 minutes passed. And it says that the instantaneous rate of change is 12 liters per minute. So since it doesn't have a sign, it doesn't say increasing, it just says changing, we're going to assume that the sign on that 12 gives us the sign on the change. So it's going to be V prime of 7 equals 12. Number 2, it says after 2 minutes, the rate which the volume is decreasing is 5. So again, we're talking about volume changing at 2 minutes this time, and it's decreasing at a rate of 5, whatever the units are. They don't give us here, but it is decreasing, so it's going to be a negative 5. And then the last one, when t equals 10, the rate that the volume is increasing is 4. So we're going to say V prime of 10 equals, it's increasing, so it's going to be positive 4. So big idea here, we want to be able to take an answer given by a derivative like we did in the first part here and explain what that derivative means. Or if we're given a derivative in some sort in a problem, so if we're given some sort of rate of change in a problem, understand what that means in terms of a derivative. So write that derivative numerically.